Like how fine-tuning a pre-trained language model can improve relation extraction. And so when I talk about relation extraction, so we mainly focused on binary relation extraction. So given a sequence of tokens and two entity spans or containing proper nouns, then we want to identify like what the relation between those two entities is. And so the main motivation behind that was that we wanted to address current limitations of relation extraction methods. I mean, so first, they usually rely on explicit features like part of speech or dependency information, and we hope that we could replace that somehow by more implicitly computed features, and so therefore limit the reliance on the domain. Also, they require a large amount of labeled data, but this is generally not only a problem of relation extraction, and learning with limited data is obviously a major concern. And then the third thing is that they often have very task-specific architectures, and we hope that that we can actually make it more task-independent to, for example, further integrate knowledge. And so our approach, what we basically did is we took an OpenAI generative pre-trained transformer with a custom input format, and we fine-tuned it to the relation extraction task, while at the same time also addressing overfitting and so catastrophic forgetting. And the language model basically then hopefully yields the implicit features we need to replace the explicit linguistic features. And it also provides us with a very generic architecture that can, for example, then be used in further work to add supporting facts to inform the relation classification and enable further reasoning steps. Yes, so just a little bit of spoiler. So yes, it does actually improve supervised relation extraction performance, and we are also able to considerably increase the sample efficiency. But so there are also some limitations. So for example, we observed that for certain entity types it actually works very well. But for others, we still need some guidance, so to guide the training process to actually achieve good performance. Yes, that's it. I hope if you have more questions, then please come to our poster. And that's it. Thank you very much.
Hello everyone, my name is Minas Krasakis, and I will present to you our work on semi-supervised ensemble learning with weak supervision on the task of biomedical relationship extraction or classification. So what's the main problem that we're trying to solve here? The main problem is that training labels are very hard to acquire for many machine learning applications, especially on relationship extraction in the biomedical sector. And more complex tasks require more complex model and more training data. So what's the main idea of about tackling this problem? The main idea is to combine semi-supervised and ensemble learning using weak supervision. And basically what we do is that we use pre-trained machine learning models as weak sources of supervision to extend training data sets. And effectively, what we're doing is that we're trading off label quality to gather more quantity of labels. So how does this architecture look like? We start from a small labeled data set. We train multiple base learners on it. And then we use a big unlabeled data set and take the predictions out of it. Then we use a denoiser, which is based on the prediction matrix, produces probabilistic weak labels. We use 3 different denoisers here, but I cannot go into more details due to time limitations. And then we basically take those probabilistic weak labels and train a big complex meta learner on them using the previously unlabeled set. If we have a look at the learning curve in this scenario, we can see that when we start from the small gold-labeled set, as we gradually increase the labeled set with much more weakly generated labels, the performance improves. And also, we are able to see, because this was a small scale experiment where we also had the gold labels for those, that the performance was achieved was comparable with with the performance that would be achieved if we used hand-labeled training examples. Now, challenges and future work. Obviously, one big challenge here is constructing and selecting diverse but also accurate base learners. Also, evaluating the different denoisers, which boils down basically to the evaluation of the weak probabilistic labels themselves, but also the generalization of the base learners to new unseen examples. And here, the thing is that basically the labeled and the unlabeled data sets must be drawn from the same distribution. And named entity recognition also here plays a big role. Thank you.
Hello, everyone. I'm Adrian Boteanu. Didn't want to skip that. I'm part of Amazon Search, and so we're a team that basically anytime you search on Amazon anything for products, you hit us at some point. We develop knowledge graphs for searching for shopping advice, so not just for products, but for advice. And we've been looking at most areas discussed in this conference. Of particular interest for this paper is how to get synonyms for them. So you may be familiar with Wikidata style of knowledge graphs. They have entities, they have many names. Sometimes the names are in emoji, and of course in many languages. And the difference between this and what we're working on is that these are made-up entities. So in Amazon, you can browse for products, and these are designed by people how they think the domain should be modeled. So the left-hand side is devices to detect fish when you go fishing underwater, and the other one is coffee, whole bean coffee, so they're quite different, and there's a never-ending list of them. And so we assume that they don't occur in corpora, and instead of trying to find them in existing text, we thought of let's just generate them. So we model it as a structural similarity problem, where each node needs to be coherent with the rest of the taxonomy. And I have other examples. You can see this is quite fine-grained, where nodes may be added because they have an additional feature or a different user or a different purpose. So it's a lot of different reasons in the same taxonomy. So our approach is to generate candidates and then filter them with a classifier. For generation, we use two methods, either search keywords or WordNet as a thesaurus. When for the synonym classifier, the poster I'm going to show basically find that, yes, it of course helps to take into account the broader structure instead of just local features. We show results in 8 different domains, from clothing, electronics, shoe, sports, pet supplies, etc. We looked at transfer learning, so training on one domain and predicting on the other. And yeah, all of this was with mechanical Turk data. So see you at the poster. Thanks.
Hello, welcome everyone. My name is Huda. I'm here to present the following papers on behalf of my research group in the University of Liverpool. They are not here due to visa issues. So the first paper is about the task of cross-sentence n-ary relation extraction by simply combining two types of neural network, the LSTM and convolution neural networks. Is written by Angrosh and Danushka Buligala and their colleagues. So simply the task is, as seen in this example, given a text span that includes a set of entities. Here we have like a gene, a mutation, and a drug, where they are related by a response or treat relation. So this text span consists of two consecutive sentences. So the task is given this set of, the set of entities and a text span that consists of one or more sentences, and we would like to identify the relation that exists between these three entities or more. For this task, a recent proposed method was the graph LSTM, and there is a extension for this proposed method, which is a graph state LSTM. They provide a state-of-the-art result for this task, but there are lots of limitations for using graph LSTM across sentences. First is that they are heavily dependent on features that is spread across sentences, co-references features, and further directed acyclic graph between words across sentence is not easy. It's complex to generate, and it's error-prone. And it's also not clear how these different parse trees are connected, and they don't address the error generated from combining different parse trees. So against these problems of graph LSTM, this work they try to propose a simple neural network model for cross-sentence n-ary relation extraction. And as can be seen in this figure, the layer colored by orange is the LSTM layer that is applied on word and position embedding features on the input text spans that consist of multiple sentences. And it's followed by a green layer, which is a convolutional neural network that is applied on the hidden states, which is the output of the previous LSTM layer. And finally, we get like the output softmax layer for classification. So it's a simple method, but they show great results against baselines and against state-of-the-art results. The one that I've mentioned, the graph LSTM. So, for example, this figure shows a drug gene mutation ternary relation results for either single sentences or cross sentences. And they show they can actually outperforms all different baselines. The baselines is, for example, they drop off the positional features, or they swap the order of the networks, and so on and so forth, different baselines here. And again, they shows for a binary relation, also they show some results for drug gene binary relations, where we got only two entities. And their methods also outperforms other baselines. For the state-of-the-art, also they shows outperform result, or at least comparable results with some previous state-of-the-art proposed method for the cross-sentence n-ary relation extraction. Yeah, lots of details in the paper, but feel free to present their posters. Also will be there in the poster session. So, yeah. Again, another paper from my research in the University of Liverpool, but this time is led by Mohammed Sahibani and his colleague. The paper is about word embeddings, learning hierarchy-specific word embedding using two sources of information, Corpus and Taxonomy. So jointly learning these words embeddings. So hierarchical information is important. Encoding those information in word embeddings is really important for various natural language processing tasks, such as question answering, taxonomic constructions, and so on and so forth. And more recently, word embeddings have shown some capability to encode these relational information. For example, there are a couple of research papers that shows that the distributional inclusion hypothesis, which says that the features of hyponym is actually a subset of the feature of its hypernym. And also recently, Mikolov in 2013 shows that a simple translation, and which is the bare difference or the vector offset between word embeddings, are actually capturing some relational information, such as the famous example, king minus man is almost equal to queen minus woman. Even though they show some capability of capturing relation, there are a couple of research papers, again, criticize that word embedding that are trained relying only on a corpus using the two-way co-occurrences between words are not actually able to represent relations by evaluating on different relation types and showing some disadvantage of relying only on word embeddings trained on only a text corpus. For this reason, this paper is trying to jointly learning word embeddings. They propose hierarchical word embeddings model where they use two sources of information. The first is a full path hierarchical taken from a taxonomy such as a WordNet, which shows a direct and indirect hypernym for each hyponym, and they try to make the representation of hyponym and hypernym words close to each other using some weighting measures measure how far this hypernym from a given hyponym. And the other source of information is a text corpus where they adopt GLOVE objective function that shows the co-occurrences between hyponym and hypernym in a text corpus. So they evaluate their model on 3 different tasks. The standard 2 task is the hypernym detection, which is binary classification, and the lexical entailment also prediction is another task where they try to measure the correlation between the scores generated by their methods and the scores, the gold standard human scores. They also propose a new task, they call it hierarchical path prediction, where they predict a hyponym, the missed hyponym given all its hypernym in a path. So they show improvement on hypernym detection compared to other baselines and state-of-the-art proposed method. And also for hierarchical path prediction, they show big improvement compared to other methods. Thanks.
Hello, I'm Karthik. I'm from the IBM Research Lab down in Yorktown Heights, and today I'm going to be presenting our work on answering science exam questions using query rewriting along with background knowledge. So this is Ryan and Xiaoyan's work. There's actually an interesting background to this. So we started looking at this topic of open domain science questions about 1.5 years back. And obviously, we were inspired by a lot of the work that AI2 has done in this space. And one of the things that is interesting about this problem, of course, is that it has a bit of everything for learning and reasoning systems. You have to accumulate knowledge. You have to recall information that's relevant to answering a specific question. And then you have to reason about how to apply that knowledge given that context. And so this fits in, obviously, with a lot of long-term research focus that we have ongoing and a lot of other research groups as well. I just quickly want to point to this paper that we worked on last year, which was sort of the inspiration for this work that I'm going to present. So this was actually work done with part of Andrew's group here as part of the Data Science Symposium. And this was about annotating the knowledge and reasoning types in the ARC dataset, which is the AI2 reasoning corpus and the AI2 reasoning challenge. And so this was a paper at a ACL workshop and an EMNLP demo. And as part of this paper, one of the things that we found, and again, this was some work that Rajeshi, who may be here, did along with some students, was that if you refine the query, then you get markedly better results. And the way we found this out was using this interface. Part of this interface that you see up here also collected input from humans on what are relevant search results to answering a given question. So we found that if you didn't have the annotated search results, then your performance was along the order of around 13% or so. But then if you use the annotated search results, your performance jumped to above 50%. And again, these were complex questions, not the simple questions that can be answered just by information retrieval methods. So we wanted to explore that in this work. I'm not going to go too much into the details of the underlying system or the results. We have the poster session to talk about that. But the basic idea is that given a question and some answer options, right? So multiple choice, usually you have 4 answer options. What we do is we essentially rewrite that and create a whole new bunch of queries, and we try to retrieve more evidence from an underlying data set. And then that evidence is where we look for the answer. So the idea being that instead of trying to search in an ocean, you try to get a much more relevant, much smaller pond for you to search in. And the hope is that that will boost performance. So that's the basic crux of how the system works. So here you essentially see some of the things that we tried, including trying to include background knowledge from ConceptNet and so on, so embeddings trained on ConceptNet and so on. Again, I'm not going to go into the numbers here. We do have the poster session for that. We submitted our results to the AI2 leaderboard, and we were pretty competitive up near the top. And in fact, the top performing method actually cites our workshop paper as well. So anyway, I look forward to seeing all of you at the poster session, and we can have more detailed discussions then. Thank you.
Hello, it's me again. This is my paper. Okay, so my paper is about learning relation representations from word embeddings. It's written by me and my supervisor, Professor Danushka Baligala, in the University of Liverpool. So as we know, different types of relations exist between entities, and why do we have to care about those relations? Simply because it benefits lots of natural language processing tasks, such as building ontology, knowledge-based completion, and also we can improve textual entailments. For example, if we are given a premise, a man ate an apple, a hypothesis, a man ate a fruit, because we infer is a relation between apple and fruit, then we can predict the entailment. Otherwise, if we have like antonym relation between two entities in two given text, then we can predict the contradiction label. In the literature of NLP, there are two main approaches to represent relations between words. We call the first as a pattern-based method, and the second is a vector offset method. In the pattern-based method, simply it's exploit the context in which the two words co-occur in a large corpus, and it actually shows that these kind of patterns are indicative of the relation that exists between the two words. So, for example, smoking increase the risk of cancer, increase the risk indicate that there is a cause effect between the two entities. As a pioneer for these pattern-based methods, Tierney in 2005 proposed a latent relation analysis method that that based only on the textual pattern that exists between the two related words. The main challenge for pattern-based method for representing relations is the sparsity. This method wouldn't be able to represent relation between two words if they are not co-occurring in a large corpus. And as we know, because of the Zipf's law, not most of the words occur rarely compared to others, and experimentally we have shown that lots of related words occur very rarely and not in a right configuration to figure out the relation that exists between them. The second approach is a vector offset, is simply the BERDIF, which is proposed by McLeod in 2013, when they shows that when we subtract king minus man, then the result is approximately a vector similar to the queen minus woman. And again, there are some limitations for this kind of simple offset methods. Some research shows that it cannot be generalized for other relations than those are evaluated initially, which is called the Google dataset. So when they evaluated on lexicographic relation, they shows how the performance drops significantly. So for these limitations for the vector offset method, we ask a question: is it possible to learn supervised relational operators that can overcome the given limitations for unsupervised methods such as the vector offset? So in this paper, we proposed a parameterized operator that can take the two vector representation for the related words and produce a vector that hopefully captures the relation that exists between them. So simply, we propose a multi-class neural network penultimate layer. We call it MNNLPL. It's a simple multi-layer non-linearity neural network that are trained on cross-entropy relation classification, and we shows that the penultimate layer are a good representation for the relation that exists between words. And the interesting point is that this kind of representation can be generalized beyond the relation that are used in the training datasets. So it can be represented relation for held out relations or for unseen word pairs. We evaluate that for out-of-domain relation prediction, and we shows improvement against other supervised and unsupervised methods. And also we shows results for relational similarities, where we compare the scores generated by the model with the gold standard scores, and we shows a better improvement for Spearman correlations. For more details, please come and visit my poster. Thanks.
Hello everyone, my name is Kirill, and now that you've already seen the spoilers, I will start with my talk, OPIEC, an open information extraction corpus. So first, what is OpenIA? The goal is to extract relations and their arguments from unstructured text in an unsupervised manner. So if you have a sentence like this over here, which is essentially holding information about AT&T being in Dallas and that it's a telecommunication company, an OpenIA system should extract this information in an unsupervised manner in the form of such triples. So once big text corpora are run on such systems, the result could be millions, even billions of OpenIA triples, and these turn out to be valuable resources for many downstream tasks, including AKBC or OpenQA. To this end, we present OPIEC, which is the largest OpenIA corpus to date, containing 341 million triples, which are also rich with metadata containing many syntactic and semantic annotations. So how we did this, we ran a state-of-the-art OpenIA system on the entire English Wikipedia, where we also kept the original golden links from the Wikipedia articles themselves. So if you look at this triple over here, you can see that it has many, many other contextual information. So mission record was created by Glenn Frey. You can see there's an n-ary type, there's a golden link, there's even space for time annotation, a confidence score, and so on. We also provided a lot of provenance information, including the original sentence and its syntactic annotations as well. So we also created subcorpora, both OPIEC-Clean and OPIEC-Linked. OPIEC-Clean contains more than 104 million triples, whose arguments are self-contained and refer to concepts. So this is less noisy than the original corpora, the original corpus. And then OPIEC-Linked containing 6 million triples, which have linked arguments on the both sides, like this triple over here. Finally, we wanted to make an analysis to compare OPIEC triples to knowledge-based triples, which were constructed from the same resource, namely Wikipedia. So we consider an OPIEC-Clean triple to have KB hit, when the information is potentially present in a knowledge base. We found that most of the linked triples actually do not have a corresponding knowledge base hit, and also that OpenIE facts often differ in the level of specificity compared to knowledge base facts. For example, for this triple associated musical artist, which is from DBpedia, we can find more specific open relations like B guitarist of or B drummer of, but at the same time we can also find far more generic open relations like B or half. Final takeaways, OPIEC is the largest OpenIE corpus to date, which aims to spur research in AKBC, OpenQA. It's rich with contextual metadata, including many syntactic and semantic annotations. We also release multiple subcorpora from noisy to clean, and finally, there's an analysis and comparison with Wikipedia-based knowledge bases. I would be happy to discuss this with you in more details later on the poster session. Thank you.
Thank you to all the Spotlight presenters.